Yes. So I'll introduce the Balsam Workflow Manager, um, and then I'll walk through some examples of using it on Polaris. So just a few slides here to start with. We've been developing Balsam at ALCF for a number of years. The impetus for developing Balsam was that we routinely have users who are running a collection of jobs that's different from, say, the large-scale parallel simulation MPI jobs that um, uh, we often see, which is more high throughput computing. So if you have a collection of jobs that you want to run and they're not coupled, you have many individual jobs and you need to schedule them across the system efficiently. That was a goal for us in developing Balsam. Originally, it came out of developing, supporting high energy physics workloads, where each application would run on some number of nodes, but we had a large number of those types of jobs, and we needed to be able to schedule them. And then in the case of load imbalance, those jobs might finish at different times. So we need to be able to reschedule nodes as jobs finish on them. So this slide just gives a quick overview of some of these aspects. It's often the case that people slide into this problem. They are running jobs on the system, and then they want to run many more of those jobs, and they end up building their own support for this. And we've seen this pattern enough times that we develop this support. And the idea is you describe your application in the terms that you're familiar with it, which means typically a command line and your options. And then from that, you can define any number of them. And Balsam will manage the execution of those for you. So you could define essentially an unlimited number of jobs and dump them into Balsam, and then have Balsam allocate nodes and run the jobs for you and track their status as they finish. It does this by having an abstraction to scheduler interfaces. So Balsam supports our systems that rely on PBS like Polaris, and Cobalt like Theta GPU and Theta and Cooley, and other systems that are, say, Slurm based or LSF based. Given a collection of jobs like that, Balsam can optimize their execution so that we reduce dead time, as I said, if nodes, if applications finish their execution on nodes, Balsam recognizes that and schedules new jobs on those nodes or on those cores. It has Python API and command line interfaces. So the goal is typically what you are dealing with is your command lines. And so the increment from running your application to running many instances of your application with Balsam should be as small as possible. And that'll become more clear in the demo slides that the demo content that I walk through. There can be dependencies between jobs, so you can build up complex dynamic job graphs depending on the processing hierarchy in your codes. All of the job metadata is stored in a database so that you have a record of all of the jobs that were run. You can query them, you can make corrections, you can extend the jobs and continue your work through this stored provenance in the Balsam database. Before moving to the example content, I just want to mention a couple of use cases. So what I've described is that Balsam can be used. You can think of Balsam as a queue on one of our systems. It's not a queue on one of our systems, but you can think of it that way. And you can dump a number of jobs in, and they'll be executed. In this example, we did this where we had data sets originating at 3 different light sources. And at each light source, we periodically submitted a job that would process a 40 gigabyte input data set. So that meant that for that job, Balsam managed the transfer of the 40 gigabyte data set from each of these light source facilities to ALCF. In this case, we were running on Theta. And those jobs would be run. And then the results from the runs were pushed back to the originating light source site. So we did this essentially multi-site remote computing simultaneously between these sites for over a period of a couple of days. There are various statistics here that talk about this processing, but you can, I think this example demonstrates the sort of use case that we're targeting in this with Balsam. So not only can you optimize throughput at a particular site, but also you can do cross-site processing. And this example is of large TPC simulation, comes from nuclear physics. I know this one is interesting because it was running each instance of the application on an individual core on Theta. And so in the plot, you can see how jobs were started and finished. So the throughput over time, and how that scaled in terms of number of nodes on Theta. So we're running on these numbers of nodes, but 64 instances per node. So at the 1024 node scale, you see we're running actually 64,000 instances of the application on Theta, keeping track again of how jobs run, how they finish, where we needed to refill jobs. And you see some drop off in terms of the throughput at the larger scale. In subsequent work, I think the scalability was improved beyond what's shown in this plot, and in fact extended beyond 1,000 nodes to all of Theta. So looking at the SDL workshop repo, there are details here about Balsam in general, again, introductory detail. And I put some commands here at the top that just as a useful reference in general. So the idea with Balsam is that you create a site. Typically a site runs on, say, a login node. And then you can you can define applications within that site, and then submit jobs within that site, and then submit batch jobs to run those Balsam jobs. So there are details here about how to get started, SSHing to Polaris, cloning the repo, setting up Balsam, and some supporting codes for this for these demos. So I said that the goal in Balsam is to have a very small increment from the command lines that you're very familiar with using to run your applications. And so this first block here shows how we wrap a command. So in this case, the command and its options are laid out here. Just a simple hello world example. There's a reason why I appended this CUDA visible devices in the echo statement, which we'll come to shortly. You see the definition and you see some synchronization. So if you run that code, then it will create that application within the site that you're currently operating, which you created above here. And then that application is available for you to this one create job.sh script will list the applications within the site just as a demonstration, and then create a job within there. And so you see it's using the site we created. It's declaring that it should use this hello app. It sets a working directory for the application, sets the parameter that we saw in the command template. And you can tag jobs just for convenience for later querying. There can be many jobs in the database, so tagging jobs can make it faster to retrieve your jobs. So if you do this, then what you will have is an application in the database and a job in the database. And then submitting a batch job to run that consists of this Balsam Q submit command. So I'll point out here again, we're using all the command line interface to do this. And the interface for submitting batch jobs mirrors a lot of the typical Q sub options that are used. We have some additional Balsam specific ones that specify the site, specify a tag that should be run within this job. So this batch job will pull specifically these Balsam jobs that have that tag. And it will use the MPI job mode. I'll gloss over the job modes for now. Typically, we use this MPI job mode. Once that's submitted, you can list the jobs in the queue. Again, this is only here as a demonstration. You can work through these, and if you have questions afterward, then I'd be happy to answer them in Slack. And then you can list the status of the job, the Balsam job that you defined here. And you'll see that that job will progress through various stages, including running and finished as the job completes. So that's the core of defining applications, submitting jobs, and then submitting batch jobs to run them. Based on that, we can take a different approach and slip into the Python API. So in this case, is simple Python script imports Balsam and defines a number of jobs and builds up an array of jobs. We see parameters similar to what we saw before. We add here this node packing count that says that it can run up to 4 per node, and that there's 1 GPU per rank. This is a typical setup for Polaris. And this is getting somewhat at the reason why I included the CUDA visible devices in the app definition. Having set it up this way and following from the point that I made about Balsam keeping track of jobs finishing and then restarting jobs on nodes where there's an available GPU requires that Balsam track the GPU that was assigned to that particular job. So Balsam will set CUDA visible devices for you in the context where your job runs. So for any given job, if you say 1 GPU per rank, it'll set CUDA visible devices to that GPU ID so that you're never oversubscribing a single GPU, for example. And then having built up this array of jobs, we can bulk create those jobs, and they are then available on the server to run. And they will run as opportunistically as they can on the available nodes when you submit a job to a batch job. I mentioned that you could have dependencies between jobs. So in this example, we create a single job and save it, and then create subsequent jobs. And the only difference here is that we set this parent IDs. So this sets a dependency on the prior job. So each one of these will depend on the one before it. And so contrary to the example above, where all the jobs could run concurrently, in this case, each of these 8 jobs, well, subsequent 7 jobs will wait. Each job will wait for the one before it to finish. So it will only ever run one at a time. This will be inefficient use of the nodes in this case, but it demonstrates the ability to have dependencies between jobs. So if you had an analysis application that needed to follow a simulation application, you could stage their dependencies that way and ensure that they ran in order. And in the context of one simulation job and one analysis job, that of course doesn't seem important, but in the face of thousands or millions of jobs, you can imagine dependency management being more of a hurdle. In this case, creation of these jobs is then also followed by creating a batch job using the Python API. So in this case, we specify a single node for 10 minutes using the queue and project dedicated for this workshop, and specify the Balsam site ID and the workflow tag that we've specified here. So this batch job will specifically target running these tagged Balsam jobs. And again, we use the MPI mode. So now what we've talked about is being able to define applications and jobs, and then you might ask, well, how do I know the status of my jobs? So I mentioned that jobs go through a sequence of stages, and those stages are captured in event log entries, and these are queryable using the Python API. So you can see when jobs changed from one state to another state, and any user data that was attached to the event. So you can do that to keep track of the details of the progress of your application execution. The Python API also includes analytics support so that you can create graphs that show the throughput of your jobs over time. This is similar to the large TPC plot that I showed at the start. So in this case, we are using the event log API to generate report details and then create plots from this. You can run this one after you have created a number of jobs going through these steps and see these reports for yourself. They'll just generate simple PNGs of the throughput. So what I've described is being able to define jobs that run at a particular site. And I gave an example of being able to run jobs across multiple sites. So all of the steps before this one, I think, are fully encapsulated in this repo, and you can work through them and accomplish the same thing that is done there. In this case, there's some extra setup required in order to make this example work, which is really just an extension of what you've seen above. In this case, I extend from, say, having one site on Polaris, as we did above, but then having sites on also Theta GPU and Theta KNL and Cooley, and also on my laptop. And this really brings out the capabilities of having the Balsam server. So I haven't talked about that in detail, but you have a site at next to each, say, supercomputer that you want to operate on. But you can access the Balsam server from anywhere. So I could be running, say, these command lines on my laptop, and having already established these sites with these apps, as I've done above for Polaris, I could create jobs at any of these sites using the Balsam command line, again, from my laptop or from any one of these sites. They would sit in the Balsam server, and they would be pulled by each of the Balsam sites to run at their respective site. So in this case, I'm creating a job at each one. I could then list them, and then I would see a list of all of these Hello multi-site jobs across the different sites that I have. Here we are then using also the command line API to submit jobs to the queues. So submitting batch jobs. And again, you see the this queue is incorrect. But you see that I'm using the command line to submit jobs at each of these different sites. And these will run, and then the status of all of those jobs will go up to the server. And I can keep track of those by listing the contents of the queue. And it will show me all of these jobs at each of the individual sites. I have a note here that if you are trying to follow these things with Polaris during the STL workshop, you will have to make a modification to one of the Balsam configuration files, the settings YAML file, to accommodate that. I'll just mention that I put the details here. If you run into trouble, you can ask in the Slack. And then the examples that I've shown are very simple, just to get you started with the details of Balsam. For a more interesting application of using Balsam, there is this hyperparameter optimization example, which will opportunistically submit Balsam jobs that seek to do a hyperopt for CIFAR 10. So I am near the end of my time, so I will finish, but I will be in the SDL Slack, and if you have any questions, please don't hesitate to reach out.
Thanks, Tom. Before you go, there was a question on the chat. Kaushik, do you want to unmute and ask a question?
Oh, I see the question. Yeah, Kaushik, you can ask, or I can read it. So I think there's a question in the chat about creating multiple jobs. How do I make multiple jobs run on different set of submit options, like different nodes? Scaling tests on different number of nodes. Bulk create jobs doesn't seem to be doing this. So the different set of submit options. So we try to encapsulate all of the submit options within the job description. So you should be able to set everything that you need when you create a job, say here. I listed the node packing count and GPUs per rank here, but there are other options that can be set on jobs, and anything that you would expect to be job specific should be able to be specified within this job object that you create. So that's the goal. And now I'm really out of time. So Kaushik, I'm happy to talk with you separately too. And also if there are other questions, I'd be happy to discuss those. Thank you.
Thanks, Tom. And thank you for keeping an eye on time there. Up next, we have Kyle Chard to talk to us about FuncX and Parcel. Kyle, go ahead and take it away.
Thanks, Corey. Hey, everyone. Thanks a lot to the organizers for inviting me to come and speak to you all today. This is going to be a pretty sort of, I said brief introduction to Parcel and FuncX, but it's probably going to be beyond brief. It's going to be very, very brief. So my name's Kyle Chard. I'm a research associate professor at UChicago, and I'm in the data science and learning division at Argonne. So I'm going to talk about two systems we have that we use extensively on ALCF machines and other machines around the world. We'll focus very quickly on Parcel, and then I'll dig a bit deeper into the FunkX system. So Parcel. So Parcel is a parallel programming library for Python. So we developed this probably 5, 6, 7 years ago now as a way of representing parallel Python programs on these large systems, enabling scaling from your laptop to a supercomputer, and enabling people to create sort of interesting dynamic workflows that couple together different pieces of code, where those different pieces of code might be some sort of binary application, some sort of script, some sort of Fortran thing you're running, and also pieces of Python code that glue that together. So I should say the Parcel library itself is 100% written in Python, and it's designed to be used in Python. When you create your workflow, you're writing a standard Python script that follows all the standard Python conventions, but it adds a couple of additional extensions for representing the types of functionality we need to represent. So the first is this idea of an app, which you see here on the right, which is the pieces of code that actually need to execute. So we have a Python app and a Bash app that are represented here with decorators. A Python app, as you might have guessed, runs pure Python code. A Bash app basically just wraps anything else. So it just wraps a command line invocation. The other thing we add is this notion of asynchronous futures. So because we're running all these programs concurrently, and we've got these little pieces of code that can run potentially independently or concurrently, what we do is we intercept that invocation and we return a future to the Python code that's running. And that allows us to sort of represent that parallelism, right? You're writing your code, you've got these futures coming back, you can continue working through your code. And when you need that future, when you need that result of that specific app, you can block on that result, or you can pass it as input into another app. And that starts to string together this directed acyclic graph, which you often hear about in the workflow world, of components that are running. And we can sort of go down the paths of that graph as long as we can as the results are actually being produced. So we've found from building workflow systems for the last couple of decades that this is a quite a natural way of actually representing parallel programs, that it enables researchers to sort of very quickly get up to speed. They can write Python codes, they can start stringing together these apps into these workflows and be able to execute them, and then outsource the complexity of sort of how do you actually schedule those things, how do you run them, how do you manage the data that flows between the apps in different resources. The other thing we've done is we've built an extensible backend where you write a standard Python program for your Parcel program that you're trying to write, and then you pick and choose a different execution model and where you want to run that thing. So we support about a dozen different backend systems, common schedulers like Slurm and PBS and LSF and Cobalt and others, as well as cloud systems like AWS and Google. So the idea is that you can basically just change a configuration option and be able to move your Parcel program from running on Theta or Polaris to Amazon or Google. Importantly, Parcel's an open source community. So we have about 70 odd contributors. We have a growing community. There's a link there to the Parcel Fest, our user meeting that we host every year, which we hosted a couple of weeks ago. If you go to that website, you will see dozens or more examples of usage of Parcel, and also FunkX in different scientific domains running in different compute systems all around the world. So that's all I'm going to say about Parcel. There's a link there at the bottom to a Binder notebook that you can basically run through the Parcel tutorial. You don't need to install anything locally. You just run it on your browser. You can sort of get a feel for how the Parcel library works. So now I'm going to move on to FunkX. I'm going to get my phone out so I don't go over time. So FunkX basically was an effort we launched probably about 4 or 5 years ago to try and make it easier to execute remote computing. We started to see more use cases in which people wanted to run Parcel across many different sites, different execution systems. They wanted to run something on GPUs on Theta GPU, and they wanted to run something on CPUs on Theta, or even more extravagantly, they wanted to run something at NERSC at the same time as they're running something at Argonne. And the interesting thing there becomes, well, with a traditional workflow system, you've got to deploy a lot of infrastructure. Where do you deploy that Parcel process? Where do you deploy databases, et cetera, for managing or storing things that are happening? How do you reliably connect to those remote resources? So the answer that most workflow systems have is you manually create SSH tunnels. You've got to keep those things alive to these different resources. And this is what we do in Parcel. And in practice, that's fairly fragile and doesn't work very well. How do we recover from remote failures, et cetera? So our idea with FunkX is to create a fire and forget cloud-hosted remote computing service. And FunkX, we're part of the Globus team. So a lot of what you'll hear here, if you're familiar with Globus for data management, is analogous to how things are organized in Globus. We basically use the same architecture. We have a cloud-hosted system. that we deploy on Amazon Web Services, has all the elastic scalability. That's where we keep all our state. That's where we keep the queues of tasks that need to be run. That's how we can recover from failures, et cetera, et cetera. So you can think of Parcel as sort of servicifying Parcel, and we break it into two pieces. We have this idea of an endpoint, which is similar to the Balsam site, which you can deploy on your computing resource. At the moment, it's just a little Python agent that you deploy, you pip install it and run it, and it sits there and basically can be used by you to run jobs. And then we have the FunkX service in the sky that's running on Amazon, and that's the service that you as a user communicate with. So you submit your jobs to that cloud service. The cloud service then takes over on your behalf, securely starts running those jobs on whatever connected endpoints you would like to run those jobs on. It will recover from failures if there are any, et cetera, and it can collect the results back again. And the good thing there is that, of course, by collecting those results, we have this asynchronous model. So essentially, as a user, I can basically submit a bunch of jobs to FunkX. I can close my laptop, walk away for a day or two, come back again and collect my results that have been run over that time. The other thing that's great is it allows us to overcome, like if we aren't getting an allocation on a particular machine, we just change a UUID and we can start running on another machine. Or we happen to, as I was saying to someone the other day, every time I want to use one of these big systems, I always happen to pick the maintenance day. And so it's always useful for me to be able to just change my UUID and move between systems that I have access to. So we'll just dig a little bit into the two main components here. So the endpoint component, as I said, is really designed to transform a computing system into a function execution system. On the right there, you see the instructions for how you set that thing up. It's entirely Python. You pip install it, you configure it, you start it, and you stop it. The agent's designed to elastically provision resources. So we're really trying to map the cloud sort of model of functions as a service, where you're able to elastically scale your resources based on what workload you have waiting. And we use Parcel for all of this under the covers. That's how we speak to the different systems. That's how we elastically scale our resources, etc. There's a note there at the bottom that you can share endpoints with collaborators. That by default is not allowed, because in many systems that's not permitted. But it's a mode of operation that we support in cloud environments and in sort of smaller research clusters in which we've gone through the processes with the administrators to allow it. And then what does this look like from the consumer side or the client side? Essentially, we have a client, a Python client here that you see on the left, the FunkX client. We implement the standard Python concurrent futures executor interface so we can have asynchronous execution. Effectively, all you do is you write your standard Python functions, you pass them to this executor, you tell it which endpoint to execute on. So there's UUIDs for all of these endpoints, and then FunkX will go away, run that thing, store the result in the cloud for a few weeks for you. And when you come back, you can just grab the resulting future and pull the result out of it. So in this case, the hello world result. I'll quickly say thank you to all the funding agencies that support this work. We have quite a few NSF and DOE awards that have supported the development of these projects. So onto the tutorial aspects. I've got probably 10 or 15 minutes here. So what I'd like to do is show you how to deploy an endpoint on Polaris, and then actually run through a notebook. We'll execute a few things on Polaris. So I've got a terminal here that's logged into Polaris that's probably nowhere near big enough. Let's increase the font to big. Hopefully that's somewhat visible. It's going to probably be a mess when we've got a Condor environment that's going to be half a page long. Okay, so Polaris has a very nice Condor module. We can basically load that. We tend to use Condor for pretty much everything we're doing. It allows us to sort of have sort of customized environments for the executions, for the types of tasks that we're actually running at a particular time. We then would like to create a Condor environment. I'm not going to remember this, so I'll just copy and paste it here. I'm picking Python 3.9 for no particular reason. FunkX works with, I think, anything above 3.6. So we'll create this environment. Hopefully things are running quickly today. It's always high risk to do these types of live demos, but I can tell you the last week this has been working well. So I'll install this stuff. So of course, this is a one-time cost as well. You set up your Python environment, you install your FunkX endpoint. From that point on, you can just stop and start it whenever you need to. You can leave it running, and we have elasticity in there, so you can actually configure it by default to not be holding jobs in the queue, etc. Okay, so we've got our Condor environment. Let's activate it. Okay, it's using up most of the line. And then to actually get FunkX there, we just pip install the FunkX endpoint, make it slightly bigger. Oh, I missed the keyword of install. Live demos. Install it. So I said it's completely Python, so it works in most environments. It works. I'm a Windows user, and it doesn't work on a Windows machine, but it works on Linux and Mac systems. Okay. There we go. We're installed, and now all we need to do is create an endpoint. So we'll just configure a default endpoint. Oh, actually, there's already a default endpoint. Let me SDL tutorial. Let's create this one. Okay, we've now got our endpoint ready to run. So as I said, we can stop and start it as we like. There's a configuration file that defines how it provisions nodes. At the moment, we won't get into that given the time, but we've got a lot of documentation on how you can do that. So let's start this thing up. We'll grab our UUID here. There's a bit of logging here saying about how the configuration, how the registrations happen, but this is the key thing we need to know. This is the UUID for our endpoint. As I said before, we use the Globus security model, so this is all tied to my identity. Of course, I've logged in here before. When you do this for the first time, you'll be prompted as a one-time authentication process where you'll get a URL to authenticate with the Globus auth system. You can use one of, I think, 300 or 400 different identities to actually authenticate. That caches refresh tokens, OAuth 2 tokens on your system, so you don't need to authenticate again after that point in time. Okay, so we've got our endpoint deployed. Oh, this is a page this is our documentation. This is a configuration that shows you how to use Polaris. We've got examples here for Blue Waters and Theta and Cooley, Perlmutter, etc. So you can basically just copy and paste these and change. Here you'd insert your Condor environment. Here you'd insert your allocation. And here you'd insert the queue you want to use, and then there's some configuration there for how aggressively you want to elastically scale. So let's now start up the client side. So you can install the notebook yourself, or you can run things in Binder. I like Binder because it because I don't need to install anything locally. I get a fresh environment every time. So Binder's this great service run, I think, from the Jupyter group, where you can play notebooks, and so they have infrastructure that dynamically creates notebooks in the sky for you to be able to run things. So here we are. The URL, if you missed it, was just funkx.org/binder. So you could do this now. There's actually a tutorial endpoint already configured. So if you're following along at home, you can just go to that URL, run through this whole thing without even setting up any infrastructure on Polaris. Let me just note here the Polaris endpoint that I just created. Looks remarkably similar, but it is different. Okay, so now let's go through this example notebook. So the first thing I need to do, authenticate. I need to tie this user session to my identity. And of course, my identity has already been allowed on the endpoint. So this restricts which endpoints I can access and make sure it's only me that can access that endpoint. So I'll go and log in through the familiar Globus auth system if you've used this before. Used my UChicago identity. I've already logged into UChicago today. I approve the access, and it gives me a one-time token that I can basically go over here and tie these things together. So at that point, I'm authenticated. My identity is mapped. I know now that I can access that endpoint. So what does this look like from a user's perspective? As I said before, basically it's just Python. So we're defining functions. If I want to change this thing and change what's being returned, or I want to import some library, I want to import platform and say what platform I'm actually running, I can do things like that. Of course, doing this live is high risk. I think this is a function. Hopefully it is. Let's try and run that. So what I've done is I've registered the function in the sky. I've got a UUID for that function. I can now come along and execute that function. Okay, so I can pick here. I want to run it. I'm just saying which endpoint I'd like to run on. I'll pick the tutorial endpoint to start with, and then I'll change it to Polaris to show you we can run in different places. So let's run that thing. Again, asynchronous. So what's happened is we've told funkx go and run this thing on the tutorial endpoint. If the tutorial endpoint was down for some reason, funkx would sit there continuing to retry to make sure it would, as soon as that tutorial endpoint was online, it would execute it again. But I would hope the tutorial endpoint's online. So let's now grab the result. And we see here, this is the junk I just put in there, as well as the platform that it's actually running on. So now if I want to change this, I've just run this on our tutorial endpoint, which is running in a Kubernetes cluster actually at the University of Chicago. If I want to change this to run on Polaris, I go and change the UUID, go and run that. hasn't yet finished. So by default, if it hasn't finished, we express the life cycle of where the task is in the ecosystem as an exception. We're gonna change that, but at the moment, that's the model we have for representing the life cycle. So you see here now this is actually run on the Polaris endpoint. So it took a little bit longer to run that than it did on the tutorial endpoint. So let's just make all of this run on the Polaris endpoint because we can. Let's paste this. Oh, I'll just paste Polaris endpoint everywhere. Okay, so if we want to think about, so your next question would be, well, that's well and good. I don't have too many hello world functions I want to run. What do I do if I want to pass an argument? So again, it looks exactly like any other Python function. I've just defined a function here. I'm going to say it takes a bunch of items, a list of items, and I'll return the sum of it. Oh, I don't want to do that. I'm going to register that function again, passing it in. And now I'm going to say, let's run this thing with a list of 1, 2, 3, 4, 5. So let me change that to Polaris. Knowing that this is asynchronous, let me just let me run that, and now I'll create a new cell to grab the result because I know it's going to take a second to actually run. I come back and I can get the result out of it. Another question would be, what happens if I want to deal with dependencies? And one of the problems you have with this type of environment is it's very difficult in a Python environment to work out all the pieces of context that could have gone into a function. So to make sure that we have sort of reliable, robust functions that can be executed, we ask that users put all of the import statements, they reproduce them inside the function so that we have a fully encapsulated thing that needs to be run. So if we have one here, I guess you saw this when I updated the one before to use platform, but if we import the date time module, we get today's date, we run that. This time I'm running it on the tutorial endpoint because I forgot to change it. And then we go and grab the result. We see that the date is the 6th of October. Another thing that we've really focused on, so both in Parcel and FunkX, has been this really strong focus on Python. We've observed that much of the sort of scientific user community has moved towards Python as a front end, as an interface for dealing with much more complicated back-end systems written in different languages. And so we've chosen to make this only execute Python functions. And so the question would be, well, what if I've got some other piece of code that I need to execute? And much like the Parcel answer, essentially your Python function can exec whatever it would like. So here, if we want to run some process and call the echo function, let's run that thing. Oh, I've got to be better about where I add these new cells. Can go and grab the result there. And so that's just using echo to print hello world, which is being captured and sent back again. Of course, I'm running this on the tutorial endpoint. I can change that and say I want to run a Polaris. I don't know if anything would be different. Oh, I ran it too quick. It hasn't yet run. Let's run it again, and then it comes back again. I'll skip through this one, catching exceptions. You can basically run something. I guess I can run this. Runs tutorial. It'll run pretty quick, I think. And so you see here that this time, I've written a function here that just raises an exception, just to show you what happens in terms of how this jives with the Python ecosystem. So you see here the response comes back, and you get a serialized version of the actual exception that's been thrown, my deterministic failure. The next example is what happens if I want to run something many times, which is the most common example of things that people want to do, right? So here's an example, a Monte Carlo brute forcing an estimate of pi. We can basically register this pi function that's throwing dots in a circle and working out how many are inside or outside that circle. We register it. We now run it 3 times. We wait for the results, and then we aggregate them to produce an estimate for pi. So if we run this, we could actually run this across multiple endpoints. So I could run 2 of these on Polaris and 2 of these on the tutorial endpoint. I'll just run that on the tutorial endpoint for now. Wait for it to come back again. I get these 3 different estimates that are different level of accuracy. I aggregate them and get a slightly better version. Of course, I can run this again on Polaris if I'd like to. I'll wait a minute for that to happen. We get slightly worse, slightly less accurate results. Okay, so that's the main way we use Parcel. The main way we use FunkX. I give too many Parcel tutorials. The final thing I wanted to show you is just how we use this executor interface. So up above, we were following the more traditional FAS, function as a service model, register a function, run the function. We provide this sort of more optimized path using the Python concurrent futures asynchronous executor model. And if you've used concurrent futures before, you'll be very familiar with this. We basically define an executor, and then we can on the fly pass in whatever functions we like. So it's like we're binding together that registration and execution piece. So if I want to double 10 numbers, I can basically just submit it 10 times. I collect a bunch of futures in a list, and then I can print the results of it. So let's actually run this on Polaris again. I'll run that thing, and I should have 10 different functions actually going and running concurrently on that system. There's some other stuff in this notebook that I'll let you explore in your own time, and there's some other notebooks as well in this binder repository to dig a little bit deeper, things about it's a cloud-hosted service, of course, so we can register and we can introspect or interrogate our functions that are registered, our endpoints that are registered. We can find out information about our endpoints, so we can see how they're configured, etc., how busy they are. So you see here some information about the configuration of, is it active, how many workers are there, how long's it been alive, etc., etc. What's the strategy? We do a lot of work with containers. So how are we using containers at the moment? We're not using containers on this endpoint, but you can configure your endpoint to use containers. So with that, I'll end. I know I've only got a couple of minutes left. Thank you for the time. Please let me know if you've got any questions. Both Parcel and FunkX are open communities. There's open Slack channels for both, and I'll hop on the SDL Slack as well if you have any questions.